Okay, yeah. So from today we'll be starting linear regression, which is a very like literally very vast topic. So we'll be starting in some parts. So the first talk, we're talking about the basics of linear regression. That what do we do actually in this? Okay. So okay, cool. I have mentioned earlier and I've told about you that we split the data, so we will train the data on the training set. Okay, so yeah, you can see the training set. So we have some sort of training set which we give to the learning algorithm, which will be bit and which is like pre-built from some libraries. So we have a learning algorithm, and in learning algorithm we give to a function. Okay, so in function we give the input x, which are the features, and after the function we get the output y. Okay, we get the output y, we get the predicted value. So you can see the visual representation. Okay, before that we have some sort of data like this. You can see, let's suppose this is the x, this is your x, and this is your y. Okay, so if you give 140 to this function, you will get 16. Okay, 16 is the original value which has been set earlier, and you have to predict that you have to get 16. Okay, yeah. So uh, this is, yeah. This is the visual representation. Okay, so you can see all this dot, these all dots are the data. Okay, these all dots are data. This all these are data, and this line is the predicted value which has been predicted by the model, that what the value of uh, the algorithm which has give us, okay, which has given us by the algorithm. Yeah, so we'll start by basics. So the basics are yeah, okay. So these are the data: 140, 200, 25, 210, 150, 200. These all our data, and this is in enormous amount. Now we all know that. Okay, yeah. Okay, so we can say that if we have to get all the data, we can say that we can use the summation. Okay, xi. Yeah, from starting from 0 or 1 to n. Okay, so this is our the representation of data. If we have to represent all the data in the like series, that we have to get the data, so this is kind of representation. So this is the I have written it. Okay, so this is your yeah, this is your what it is. Yes, it's the number of bedroom. We can say that it is the target input variable. Okay, this is the feature or the input variable for which of the data set xi. The xi is the input for the function, for the function. Yi is the output for the function. Okay, so you have a representation. Okay, so the question is, how will you get this line? Okay, how will you get this line? Okay, so if we have seen this, all these points are data, these all dots are data. Okay, these all are the data points of what our data is representing. Okay, these all are these points. Now this is the line which has been predicted by our model. This is the line which has been pre-predicted. There can be line like this also. This is not a good representation because we want a line which is have less error than ever. Okay, so let's suppose we have a line like this. You can see this line can't even align to the data. Okay, you have like this, the data points are very far from it, like our data is so close but another point is like very far. This is very far, this is, so your error rate is very high, so you can't even rely with this line that you have a good model. Okay, so you have to like tweak the data to get what the perfect line, the fittest line you can have, which can give you the data in the perfect way in the future, because you're building for the model for the future problems. Yeah, so let's suppose we have a line like this, we have another one like this, and like this. So from the visual graphical representation we can see this is the best line which we want, this is the best line which we want. And and to get this line we have a equation which we have studied in our school, which is y y equals to mx plus b. Okay, so if you give x to this equation, then you'll get y. Okay, you'll get this y. B is like coefficient which is like uh, given before, and m is the slope. M is the slope. Yeah. So if you see this point, you will say that the line is here and the point is here. So this is the point which is predicted by the model. Okay, this is the point which has been predicted by the model, and this is the original point which is our data. Okay, this is the original point which is our data. Now you can see this distance. Yes, this distance we call as error. Okay, the error, because this is not a like perfect model which has been built, so this is the error which we have got. Yeah, so this is the error, and this is we say this is the residual. Okay, this is the error, and this is what you call is a residual. Okay, so I have like notes open in front of me so I'm like not like that I'm very good at it, so I'm like teaching you with this. Yeah, so so yeah, one second. Hmm, this is where the ground truth. Yeah, yes, this is so the value we can get. So this is the point. In this term we say it a ground truth. What we say, it's ground truth. Okay, this is the predicted value. If we say this is our predicted value, this is our error, and for like every point we have some kind of error. There is some point which is like exactly aligned with the line, but we have some kind of error which we have to see. Also we have to like take consideration of it also, because it is very important thing for us. We have to measure the error, that how far we are from the actual data. So first of all, we have to see how we get this line. Okay, we can't get a like perfect line in the one chance. Okay, so what we do actually is we give data to this function. Like let's suppose the function for like historical regions, we call this function hypothesis. What we call it is, this is called hypothesis. Yeah, so this is the hypothesis function in which we input x. Now we have some parameters like theta 1, theta 0, theta 1, and x1, because we have only one input. So we are have only like two terms. Okay, this is our two terms. So this is this term, and this is the coefficient. We know, as we have seen the equation, that we have some kind of a coefficient which aligns with the data and aligns with the line, which makes the line like linear. Okay, because it's linear regression, so we must have something linear in it. That what is the way of talking to linear in it. Okay, so yeah, this is what we call is parameter. What we call it is parameter. This also we call a parameter, and this is what we call also is weight. Yeah, this is what we call is weight. So we got this. This is called parameter and weight. Now you have the weight, you have the parameter, and the value you're getting, the y. Okay, so y, we can say the y the predicted value, which is like h of x. This is what it is. Okay, so you will get h. You won't get perfect or exactly to the same. Okay, you can't get the function, and you give let's suppose you gave the data to the function and you can't get the exact number what you want. Okay, you can't get like this. What you'll get is approx to y. Okay, you have to find that coefficient or that's variables that approx to y. Okay, you have to get the uh, result which is approx to y. You don't have to get like which is equal to y, but you have to get which is approx to y. Let's suppose your y is 16 and you are getting 14.9 or 14.6, which is like much better than having a 16. Okay, because like if your model is like totally perfect, we can't say it is a good model, because how can you be perfect at the right time? Okay, if then you have some done some error. Now you got the equation which is hypothesis, what we call is theta 0 and theta 1 and x1. Okay, so x1 is the input, theta 1 and theta 2, this is a mission. Okay, we have to find it in way that we get the y, okay, the predicted y, the y which has been set. So we have to find this theta. So the question rises here, this how do we find this theta? This is the biggest question. Okay, how do we find the theta? We'll be talking about this in later thing, uh, later parts. But the thing is that you have to get that you have to predict h of x which is approx to y. Okay, you have to predict y which is approx to h of x which is approx to y. Okay, now you have to measure also. Okay, yeah, so this point is coefficient in this equation, we call it intercept also, we call it intercept also, and we call it weight. Now you have some error. Okay, have we seen earlier that we have some kind of error which we have to consider also, because if you don't like consider error then you'll having a very bad model, so you have to consider some error also. So you have a function which consider the error, that how our error is, like how the amount of error and how far our data is. So how will you consider the error? So you have a function which is called cost function. What do we call it? We call it a cost function which consider the error. Okay, which consider the error, and we give this error like j of theta. Okay, the error is, let's suppose we have some kind of we have some g of theta, which is like we have to give some theta and you will get some error. And how will you get it? So let's suppose the predicted value we have. Okay, so we have, you know that if we our the original point is 16 and we got the our point is 17, let's suppose we guess the number is 17, then we are minus 1. Okay, so we are minus 1 because we guessed 17 and the original value is 16, so we are like above 1, so we have to minus 1 to maintain that flow, that what the actual need is. Okay, yeah, cool. Now the cost function, what cost function do is it uh, yeah, to formalize the clause, yes. So the theta, this function take only this function only care about how far our data is. We have to consider also, because let's suppose the value we got. Okay, so we got, let's suppose this is summation, why the hell is like summation I equals to 1 and to m. So you have hypothesis, the function which we talked about earlier, and this is the x, and this is the subscript. Okay, this is the like super subscript. We know about the subscript, the subscript and super subscript. These are the things. So we don't need it. It don't relate to exponent, because like let's suppose we want to, then it's nothing. We're gonna talk about the exponents, like it's gonna be a power of 2 3. No, it's not like that. It's that representation of that which number, the which portion, like which number with nth term it is. Okay, this is, we gave this hypothesis function as we talked. This is the hypothesis, our function hypothesis function. And now we'll minus 2 with the I. Okay, the predicted value, the predicted value, this is a predicted value, and we'll get about that how far we from the actual point, and we square it, because if we get the point in error, if we have get in the minus, then we have to like make it positive, because if we have some kind of minus negative value, then we'll end up having some loss in our number which will we get. Yeah, cool. So let's summarize what we have learned right now till now is that we have a function. Okay, we have a function which is called hypothesis. We have a function which is called hypothesis function. Like, let's summarize what we have learned is, okay, so we have a function hypothesis in which we input x and we get what we get, theta 0. Okay, so this is the coefficient, we'll or the intercept. Okay, coefficient or intercept, which is playing a major role in like getting the line. And the next thing is theta 1 and the x1 input which we got. Okay, which we gave to the function. Yeah. So this is the function from which we'll get the line. So let's suppose we're getting the line like this. We're getting the line like this. Okay. This is the data point and we got the line like this. Okay. Now we have a hypothesis function and we get some errors. Yeah, actually we'll get some errors. We're not gonna like be predicted so perfect that cause okay, hey, 1 second. Yeah, this is not gonna be such that predicted thing, original thing. This is not gonna be that exact, so we have to predict in a way that our h of x is approx to y. Yeah, our h of x is approx to y. Now we have to take care about the errors also, because errors also. So we have a function called cost function. Now this is a function like which care about only the errors. So how will you get the error? You'll need to minus the y-intercept y from the value that has been predicted. Okay, so the value which has been predicted is h of x. You'll get the value and minus from y. Okay, and for every point, for each and every point we'll minus it, so we are gonna add a subscript, sorry, superscript. So we have this and we'll square it, because if there any negative thing, negative value, we'll end up having losing the data in some less amount. And next we'll add this, sorry, we'll add this to n, and we'll have 2. It's like it's given, but we'll talk about it later. And this, hence we have got the error. Okay, now we'll be doing later. So this is our the summary. So we have the data. So yeah, so I'll be seeing you in the next one. Okay, bye.